looks like it's 2 o'clock Eastern. And I just wanted to welcome you all and thank you for joining us. My name is Ana Becerril, as you probably know. I want to thank you all, and especially I want to recognize today because it's the last day of the seminar for the academic year. And I just wanted to take a moment to recognize the work of the organizing committee, who is chaired by Thanasis Saltis, who is your host today. And also we had representatives from all of the IRENA networks, Tyler Gorda, Seija Hayakawa, Mohamed Mardini, and Chiranjeev Mundal. They all work hard in putting a really good program for the year, and we have a great lineup. It will run smoothly, and we were very happy with the results. So thank you very much to everyone, and especially Thanasis. And also I want to recognize Rahul Jain from MSU, who is the representative of the Young Researchers Organization, and he was in charge of the prep sessions every the beginning of each, previously to each seminar, which was very helpful for grad students and postdocs to get familiar with the topic of the seminar. So I just want to say thank you to everyone, and I will be very happy to receive volunteers for the next academic year. So take it as an opportunity for networking and for some visibility with the IRENA network. So that's all, and Thanasis, please take it away.
Okay, thanks, Anna. So hello, everyone. Welcome to the last IRENA online seminar. Today we have the great pleasure to have Professor Michael Wiescher with us to talk about his latest research projects. So I guess there's not so much need for introduction for a person like Professor Wiescher, but I'll give you just a brief overview. So he's a Freiman Professor of Physics and Director of the Institute for Structure and Nuclear Astrophysics at the University of Notre Dame, and also founding director of JINA. And recently he received this prestigious Wolfson Fellowship from the British Royal Society. And he's serving as a visiting professor now in Europe at the University of Edinburgh, where he wants to expand the collaborative network with other European institutes. And there's a lot of work going with in other facilities, such as in the Gran Sasso in Italy, and acquiring a GSI in Germany, and also France, a neutron beam facility at the University of Frankfurt. And all these large-scale collaborations are within IRENA, in which Professor Wiescher is also one of the principal investigators. So Professor Wiescher, if you're ready, you can share your screen, and I will ask you to start your talk. So the talk is about CNO cycle and neutrinos. So it's really exciting. We're looking forward to it. And again, thanks for taking your opportunity to give this talk today for us.
Okay, thanks a lot, Thanasis, for the introduction. And I'm very pleased to see so many old friends in the audience, so I'm a little bit baffled about that. But anyway, it's not so much that it's my latest research project. It's literally something which I've done since many years. I literally returned to my roots with this project and with this talk about the CNO cycle and the CNO neutrinos in our sun. I want to, on the right-hand side, I have the list of the topics I want to address. Reintroduce the standard solar model. Not everybody may be familiar with it. Talk about the solar metallicity and what it is, and how it determines the CNO cycles in our sun, small percentage of the solar hydrogen burning. And then I will get to the experimental part, talk about the Caspar laboratory, which you see a picture there in front of you, and what we did to improve old measurements of CNO reactions. Talk about then how that correlates to the CNO neutrinos, and about future efforts which we're trying to start in the next few years. So here you see basically the Wikipedia picture of the standard solar model. You see the core, 10 to 20% where the main activity of the hydrogen burning takes place. You see the standard formulas. The luminosity is of the sun at the surface is defined by the energy production in the center minus the neutrino losses. And according to the standard solar model, the temperature is about 15 million degrees and the density is about 153 grams per cubic centimeter. And our problem is when we look at the sun, we don't look at the core, obviously, but we look at the outer regions. So we have to, for the understanding, we have to take into account the energy transportation processes, absorption processes, all sorts of things to extrapolate from the surface to the interior. And that is being done with applying of standard solar model. For observation, we have roughly three tools available in modern times. The first is the classical tool of spectroscopy, where we look, developed literally the two last centuries, where we look at the elements by absorption lines and things like that. So that gives us the elemental analysis of the surface of the sun, not of the center of the sun. More recent is helioseismology, where we use the sun as a resonator and look for vibrations in the sun triggered by solar activity at the surface. And the analysis of the vibration gives us information about the densities distribution and also to a certain extent of the distribution of more massive elements. And then finally, the sun as neutrino source, and that is basically the way where we can look directly into the interior of the sun because neutrinos are only produced by the nuclear reaction taking place in the center of the sun. And that can be visualized like on the picture here from Kamiokande. And that gives us a direct information and maybe isotopic information about the solar interior. So here's a standard solar model, sort of an overview, a colorful picture on the top left side with the different spheres of the photosphere, the chromosphere, different solar activities at the surface, sunspot, prominences, flares, and things like that. And then you see the temperature distribution starting from the core of our sun. That's basically the radius, a fraction of the radius to the total radius. And you see here in the center, you have about 15 million degrees, and it declines rather rapidly to 10 million degrees here at the sort of outer fringe of the core. And then you have sort of this decline to the surface, which is basically described by these formulas. Correlated with that is the decline of the density, about 150 grams per cubic centimeter in the center, and it declines rather rapidly. Here is the solar abundance distribution. That's the older one, that's by Anders and Greves. There are new ones, and that is actually part of the problem, that there are discrepancies in our prediction or tabulation of the solar system elemental abundance distribution. And you take the standard solar model, then you see the distribution of the light elements, hydrogen and helium, as a function of radius here in the center. And from that, you can see that we are about one half-life into the solar life. So hydrogen is being depleted to about less than 40%, 50% of its original value, and is being converted to helium. And you see basically helium goes down, and it's on the original value of the classical solar abundance distribution on the surface, but here that's the source of the stellar hydrogen burning. For our topics, it's even more interesting to look at the more heavier metals and so-called metallicity, and that are primarily carbon, nitrogen, and oxygen. You know, astronomers use metallicity. Metals are everything above helium. So, and the most abundant heavier elements are carbon, nitrogen, and oxygen. And you see in the center, the carbon is depleted and is being replaced by nitrogen. So we expect, or the standard solar model expect, the primary heavy element in the core of our sun to be nitrogen-14, and carbon-12 is being depleted. So let's first talk about the energy source. The main energy source of the sun are the pp chains. That is very well known. And here you see literally a Wikipedia presentation of the pp chains. Two hydrogen atoms fused by the weak interaction that warrants the long lifetime of our sun. And it's a weak interaction process, so neutrinos are being produced. You produce deuterium. Deuterium captures a proton, forming helium-3, and then either two helium-3 nuclei fusion, forming helium-4 plus 2 protons, or helium-3 interacts with the existing alpha helium abundances, forming beryllium-7, which goes into either by electron capture or proton capture, forming the second and third CNO cycle. So since there are a number of weak interactions are involved, you expect neutrinos. That has been predicted pretty early. And here you see basically the expected neutrino spectrum from the pp chains. Beryllium-7, that's the electron capture, so you see sharp lines, and then the boron-8 from the beta decay of boron-8 to beryllium-8, which then decays into alpha particles. That is basically the neutrino budget, the neutrino energies, or the endpoint of the energies for the beta decay. And that can be visualized, as we just seen here. That's the image of these neutrinos as detected by the Kamiokande detector in Japan. The first measurement of the solar neutrinos was a Ray Davis experiment that was many years ago in the 60s or so, 70s. And that was based on the installation of a $100,000 gallon tank of perchloroethylene deep in the underground in the Homestake mine, about a mile down. And it was literally cleaning fluid, lots of chlorine. And the idea was that the chlorine 37 would interact with the neutrinos, converted into argon-37, which is a noble gas, and can be literally diffuses out of the liquid and can be detected. Here you see basically the results of the different runs and the average value. And as you can see, it's far lower than the predicted standard solar model value, about a third of it. And there was a lot of activities in why is that discrepancies. A lot of people argued that it's a nuclear physics problem, so the nuclear reaction rates are far. Other people argued for different reasons. And eventually that was the birth hour of the neutrino physics field, where it was predicted that we have neutrino oscillations with the electron neutrinos being produced in the sun, being gradually converted on their way to Earth into tau, and as you can see here, muon neutrinos. So that's, of course, neutrino physics, which really is subsequent activity to our field of the nuclear astrophysics. So that's only for introduction. So when you look at the energy production of the sun, plotted here as a function of the solar temperature, and you look at the energy production of the different hydrogen burning processes, then you see here the PP chain, which sort of levels out due to the fact that it's a weak interaction-based problem, and it cannot rapidly enhance the reaction rates or the neutrino energy production. The CNO cycles increase the energy process much more rapidly, and you can see from this that about 1 to 3%, 2% of the solar energy is being produced by the CNO cycle. And that, of course, depends on our assumptions on how much nitrogen is in there, how much carbon is in there, how much metallicity is in there. The CNO cycle is, again, like the PP chains, were first formulated by Hans Bethe in the 30s. And you see here the cyclic catalytic process where the carbon, nitrogen, and oxygen content in the sun basically are being used, maintained, and you have a sequence of proton captures, 4 proton captures, which gradually, with some final alpha helium emission, which gradually convert the hydrogen fuel into helium. And you have also 2 neutrino sources, or in principle 3 neutrino sources. Here in this so-called first cycle, you produce basically nitrogen 14 p gamma, you produce oxygen 15, which beta decays with about a 2-minute half-life, emits a neutrino, you can detect that, and carbon 12 p gamma produces nitrogen 13 beta decays, and you see the neutrinos. And here you see basically the neutrinos plotted into that neutrino spectrum. You see nitrogen 13 is less energy than O15, and fluorine 17 is basically from the second CNO cycle, which we don't want to consider. It's much weaker here. So you can calculate the budget on the basis of the standard solar model, and that are the expected numbers. And that depends, these numbers depend pretty much on our assumption of the CNO or on our prediction of the CNO abundances. That's what I learned from Friedel Thielemann doing reaction networks in my early youth. And you see basically a simplified reaction network for the CNO cycle, the change of the abundances as a function of the reaction rate. Here, for example, nitrogen 13 is basically depleted by its beta decay and produced by carbon 12 alpha p gamma, and O15 is depleted by its beta decay and produced by N14 p gamma, which happens to be the slowest reaction in the CNO cycle. So you have a balance, and it depends on the reaction rate and obviously also on the abundance distributions. When you run that for constant temperature and density of the sun, so you see basically carbon 12 is depleted after some 50,000 years and converted into nitrogen 14. Here's nitrogen 15. So you establish an equilibrium abundance when you are in an equilibrium hydrogen burning environment. And that is the idea of the sun. So we operate on an equilibrium abundance of the CNO elements. When you have an equilibrium abundance, so the change of abundance is 0. So you basically can equalize the production with the depletion reaction, and from that you can easily calculate the abundance ratios in the framework of the standard solar model. So that's how it works. So that's how we can produce basically, or can calculate, estimate the ratios of carbon 12 versus nitrogen 15, carbon 13 versus carbon 12, etc., etc. So what does it have to do with the solar neutrinos? The solar neutrinos, CNO neutrinos now come from the decay of nitrogen 13 and oxygen 15. So the abundance of these two elements are important, and as I just mentioned, that's determined by the abundance of the N14, because N14 P gamma produces O15 and carbon-12 P gamma produces nitrogen 13. And here you see basically the abundances of all the CNO elements as a function of radius. Here you see what I showed before. Carbon-12 is pretty much depleted in the center of the sun, and the metallicity has shifted to nitrogen 14. And then at the borderline of the core, you see there's a drastic shift, and that is basically the initial abundance distribution towards the outer radius. And yeah, this is the temperature, as I showed before, and that is hydrogen and helium. So these values basically allow us, using the formalism as shown before, to calculate the O15 and eventually also the nitrogen 13 ratio, and therefore the neutrino rate. So the neutrinos from the CNO cycle, at least one kind, has been recently measured over the last few years. And these measurements were done at Borexino. It's a liquid scintillator detector array deep underground in the Gran Sasso. You see basically here the picture, a spherical array. Was a big sphere filled with a liquid scintillator, which caused some trouble because they had a leak and caused major concern for the water budget of the Gran Sasso mountain massif. Anyway, they were allowed to continue, and that is basically the measured neutrino spectrum. The challenge with that is these detectors have limited resolution, and you have to analyze and extract the critical neutrino rates. And here you have numerous contributions. You have basically from the PP chains, the PEP neutrinos, you have neutrinos from the decay of natural radioactivity, bismuth-210 or carbon-11, which contribute here. Basically, each of these lines represent a contribution, and the critical one is here is the decay of carbon-11, which is a cosmic ray-induced or radioactive decay induced in the rock material. And here in red, you see basically when you subtract and analyze this spectrum, subtract all the different components, you are left with here the red line, which is supposed to be the neutrino signal from the decay of O15, of nitrogen 13 would end basically here. It's largely handicapped by the increasing background. So the claim is that they see primarily the neutrinos from O15. The neutrino detection was converted into a neutrino rate, and it comes up to 7 + 3 - 2 times 10 to the 8 neutrinos per square centimeter and second. There's unfortunately only a PIL published, so it's difficult to follow the details of the analysis, but the claim is that this result would translate into a higher metallicity than predicted by the standard solar model, based on the present nuclear reaction rates. That means the nuclear reaction rates are primarily N14 P gamma, but also the reaction rate for carbon-12 P gamma and O16 P gamma as other neutrino sources should be reviewed, because if we don't know one reaction rate, there can be considerable doubt about the other ones, because most of these reaction rates have been measured in the 70s, and the technology wasn't as good, and several parameters have changed, etc., etc. So how is the neutrino correlation? How does the number they measured correlate with the abundances? And I go back to the equation here of the change of O15 as a neutrino source as a function of production and decay. And from that, you can basically calculate the neutrino rate, which is proportional to the beta decay rate, obviously. And then you can solve that for nitrogen 14, so you can directly calculate the abundance. That is a claim that this abundance is higher than predicted by the standard model. So what we want to do, that's a function of the measurement, the neutrino rate, but also a function of the production rate. So what we plan to do is basically remeasure the nitrogen 14 p gamma production rate. That's not only the group at Notre Dame, but in Caspar, but also many other groups have contributed to this question. So we use Caspar, and but before I get to that, I want to give you the status of our present knowledge of the neutrino sources. On the one hand, on the left-hand side, you see the a carbon-12 p gamma reaction and a recent R matrix fit to the existing data, and you see it looks pretty good. And also the extrapolation, which is always a challenge, the extrapolation to lower energies shows a small error bar. The LUNA collaboration is presently remeasuring this reaction cross-section, trying to push it to lower energies because they are relatively old measurements, and we will see what the outcome is. There have been more activities recently in the N14 p gamma rate, and the N14 p gamma cross-section is characterized by a strong resonance at 278 keV, and then you see basically different predictions based on different data sets. So these are data sets from measurements at LENA in North Carolina and LUNA in Italy. It basically depends, it's your choice, how you do the fitting of that. I will say more about that in a second. So what are the experimental and theoretical challenges? So this is basically an overview about the N14 p gamma rate or N14 p gamma cross-section, which determines the rate, and how we extrapolate the laboratory data, which you see here up in the front, to basically over several orders of magnitude in cross-section into the solar energy range. So this extrapolation is a theoretical challenge. And it always has been a big challenge. What is a reliable extrapolation and what are the reliable input data? And these theoretical extrapolation are handicapped by model uncertainties, even in the Coulomb and barrier treatment and in the treatment of nuclear potentials and Coulomb potentials. It requires an understanding of direct capture processes and interference effects at very low energies. I mean, we extrapolate that, we need theoretical model. How do we interfere? There's coupling of bound states to the continuum or higher excited states. There are threshold quantum effects, and there, last but not least, is the impact of electron screening, which we have to correct for and which we don't really fully understand. For that reason, the measurements have to be pushed towards lower energies, and the nature of this bump has to be understood. Why does it go up again? And basically also the impact of lower energy, upper energy resonance have to be fully implemented. Here you basically see a picture how this development goes. And when you look at the old knuckle compilation from the late 80s or early 1990s, you see basically how traditionally an extrapolation of a reaction rate or the S factor, I should have said the S factor is basically literally the correction of the cross-section by taking out the effect of the Coulomb barrier. The S factor is basically extrapolated by a straight line. That's the old Willy Fowler approach, because we don't know anything, so it should be kind of straight. Now we have this that's on an R matrix simulation, which is based on data taken at lunar underground at the LENA accelerator above ground. That are the LENA data, that are the lunar data, because they are in a more background-free environment, they could push the data towards lower energies. So there's a problem. So this is interpreted as a contribution of subthreshold states which interfere with the, you see that here, subthreshold states here in this energy range, here is the threshold, which interfere with the resonances above threshold. So we don't really know the nature of the interference. For that, we have to determine the width of these subthreshold states to calculate that. And this width determination can be done by determining, by measuring the lifetime of these states. And the lifetime of the states is inverse proportional to the width. And that translates then in the cross-section. We can calculate the expansion of the cross-section towards higher energies. And we did these measurements using a method, the so-called Doppler shift attenuation method, which literally measures the Doppler shift of an outcoming gamma ray from the N14P gamma reaction as a function of angle. This is the equation. So the gamma rays are literally basically reaching the detector, and they are emitted as a function of the stopping of the recoil nucleus in the target material. So we need to include information about the stopping power, which usually carries relatively large uncertainties. Here you see basically the different Doppler shifts for the various detectors, which is a function of angle. And for that, we managed to determine the lifetimes of the various subthreshold states, and they're literally in the femtosecond range. So Doppler shift attenuation is usually used in the picosecond range. Pushing it in the femtosecond range has been attempted many times and usually failed. And while we claim a value, while we got a value, you can see our values have large uncertainties. And that, of course, translates into large uncertainties in the cross-section and large uncertainties in the extrapolation. That's basically the range of the R matrix predictions for the contributions on these subthreshold states, including the error bars. And you see it really doesn't give us any major limiting factor. It helps, but it doesn't really limit us. It tells us they contribute, but we cannot really determine the level of this. For that, we would need better lifetime measurements, but that requires a completely new method. A second approach was done some years ago in 2016 to map the contributions of higher energy states. That was supposed to be an improvement of the old measurement of Klaus Rolfs, known as the Schröder paper. He was the first author done at Bochum. And so we repeated that measurement because there were some issues with the study and the way the data was presented. I don't want to go into the details. So we literally measured here the blue points. We repeated the measurement, and this is only one example. That's the ground state transitions of the N14P gamma reaction, where you have some major uncertainty. And then we developed with Tikazuma new R matrix program, Azure, which has now worldwide use, which allows us to not only analyze the specific reaction channel, but many reaction channels in parallel, which gives the R matrix a much more predictive power. And here you see basically the R matrix fit of the N14 elastic scattering data, the ground state transition data, and higher transition data. So transition data to the 6.79 state at higher energies. And that basically allows us the R matrix to extrapolate with a certain uncertainty range. So that's the approach, measurement, and then using the R matrix in multi-channel approach to extrapolate into the reaction cross-section into the stellar energy range. And that is also a problem for us now these days. So what you see here is the R matrix extrapolation towards lower energies into the energy range of the sun. And you see basically here's a 278 kV resonance. You see the discrepancies between the UNC data and the lunar data, and it pretty much looks like we agree with the lunar data in this fit. However, when you take into account higher energy regions, the tails of these broad resonances here, tailing down and causing potential interference here in the low energy range, then you see with that kind of fit, you don't match the higher energy data. So there's a discrepancy. And that is, of course, the question of how well do we understand the subthreshold resonances? And how well do we match the higher energy data with the lower energy data of lunar? And there is literally this gap here around 500 keV where the number of data were limited, and that's where we had trouble overlapping the data. So the goal was to remeasure the data, and that was not only done at Notre Dame, was also done in Rossendorf in the Felsenkeller, and many other groups were interested in that. So we did it at the Caspar accelerator at SURF. Caspar is an old machine, not quite as old as I am, but it was literally built in the 60s. And it's still, we rebuilt it several times. I run it in Toronto, I run it in Notre Dame, and now I run it in 1 mile underground on this location here. And so it's a challenge to get there. You have to go 10 minutes by lift, and then you have to walk a mile, 1 mile down, 1 mile walk, and then you're there. This is the Caspar lab. That's the traditional reduction of background due to the absorption effects of the rock. So that's the environmental activity, and that sort of provides the background. You reduce that when you go underground. You basically lose this background here, and then with additional shielding, you optimize your setup even better. That's the same here for neutrons, which I don't want to discuss here. That is the experimental arrangement, straightforward. Here again, you see basically a spectrum above ground without shielding and with shielding. And here you see basically the setup. You have a target here, you bombard it, and you mount a big detector close to it, well shielded, and you measure the different transitions. And here you basically see the transitions to the ground state, and then secondary transitions from the excited states, which are populated at energies which are outside of the range of this spectrum here. And that is basically the excitation curves, the raw data, which we measured in several runs in the underground environment. So here for the ground state, we went from 1 MeV down, there's a resonance there, down to literally 220 or so kV. Here's the resonance, which is not included in this data set. And here's the transition to the 6.79 MeV states, and the cross sections were normalized to the well-known strength of this resonance. Measuring this resonance strength was actually my very first nuclear physics experiment, so I trust it. Now, when you translate these data and couple them into the S factor, and couple them to the lunar data, you see the following. Here's basically our new data, including the Schrödinger data and all sorts of basically the compilation of all the available data matched to the lunar data in yellow. And you see it's basically you have now a good overlap on different data sets. And here it's for the 6.79 transition, also a good overlap. So data-wise, we seem to be very consistent now. However, when you do an R matrix simulation, and you see here basically the R matrix simulation over the entire energy range, where we measured from 2.5 MeV down to something like 100 keV, you see it seems to match very good now. However, there seems to be a gap. There seems to be a drip, and here you see it a little bit amplified. Basically around 500 keV, the S factor drops and stays lower. And here even more enhanced, see the drop in S factor at 500 keV and stays lower. And I have to admit, we just cannot fit it. We fitted all the channels, we took subthreshold states into account. We fitted the elastic scatter, included the elastic scattering data, things like that. There is something missing. And the missing seems to be correlated with 500 keV with this dip in data. Anyway, this is the optimal fit. So if you take that, you can calculate the reaction rate, basically by integrating over the entire cross-section times the Maxwell-Boltzmann function. And then you get this as a reaction rate. When you compare that with previous published rates by Coughlin, Fowler, 88, by the Knuckle compilation, Angulo in 99, and then more recently by the lunar data by Imbriani et al., you basically get this ratio that our rate is about 50% smaller than the previous tabulations by Coughlin and Fowler and Angulo, and about 15% larger than the lunar predictions. But that is due to that little dip in the cross-section data, which we have not yet explained. When you take these data, however, then and kind of follow the guidelines Borexino beta gives in how to take into account the neutrino oscillations, etc., then we calculate neutrino flux something like 9 plus minus 2.5 times 10 to the 8, which seems to be in reasonable agreement with the neutrino observations. So that one has to take with a little caution, because I had to kind of guesstimate neutrino oscillations and other effects to convert our rate into their observational rate. So that is the status of this thing. So what is the future? We have to address the question of this dip in the cross-section, the unexpected dip. So one has to also address see for an improvement of the neutrino rate. You saw that was handicapped by large background contributions, but there will be no more Borexino data, no more Borexino experiment because of their accident with the liquid scintillator spill. The decision was made to shut the detector down. And as you can see, the dismantling has already started. It started in last September. So future measurements will be presumably be done by SNO or Kamiokande. I think that's other labs which are talking about these possibilities. I'm more on the accelerator side. Right now, Caspar is shut down. It was shut down from 21 to 23 due to the fact that right next to it, they excavated the made the excavation explosions for the dune detector to measure neutrino oscillation. So we are at the direct neighborhood. So people did consider it safe for us to be hanging around. So they shut us down, but we will start in next fall again in 23. And we hope to do detailed underground angular distribution measurements of these reactions. However, we are not the only one. There are several other new and very powerful underground accelerators being installed. And you can see we are from the 60s, from the 20th century. They are from the 21st century. Much better technology, much better beam intensity, and that's first Lunar MV, and they want to use the N14P gamma reaction as a characterization for starting the accelerator. Then is JINA, the Chinese competitor, in CJUL lab in I have to say Western China. Yeah. And it's a very impressive facility. It's limited to 400 kV only, so it compares to the old Luna, but they are also applying for a higher energy accelerator. And last but not least, there is Lena MV. It's a new accelerator installed at UNC and ready to go. They do above ground measurements, but they're also interested in a remeasurement of the N14P gamma reaction, and hopefully this concerted efforts here all around the world will provide better data and a better understanding of the low energy cross-section. That's a conclusion. We have good agreement in the data, but we are not able to fit it. That means we are not able to explain what the nature is of the dip. I looked around. There is, in comparison with the mirror nucleus in N15, there is one state is missing, a 3F+ state, but that is expected 1 MeV higher. So that would be an interesting nuclear physics problem to for shifting the states down. It would require a unique nuclear structure configuration for that state to explain the so-called Thomas Ehrman shift. So that's where we stand. Unfortunately, I cannot give you a final result. So it's literally something more, something like a status report. So I want to acknowledge at least some of the people. Bryce Franz, he was the PhD students who did all the work. Ani Abrahamian was in charge for the lifetime measurements. Joachim Görres, Dan Robertson, Tom Kadlecek, Frank Strieder were involved, and many other graduate students were involved in the reaction studies above and underground. James DeBuo in charge of the R matrix analysis, and Gianluca Imbriani for many discussion, and in particular when I put doubt into his reaction rates, so he argued strongly with me, and I have to apologize for questioning him, because we do agree with his data. Okay, with that, I want to stop, and I'm ready for questions. Thank you.
Okay, thank you so much for this wonderful talk. Okay, so now let's move to the questions. So you can either raise your hand or you can write on the chat. Okay, yeah, Friedel has a question, please.
You had some intermediate result, and I'm not completely sure if I interpret this correctly. With this changed cross-section you have at the moment, you can explain the Borexino data with the old solar system abundances, and you don't need an enhanced metallicity. Is that correct?
That's correct, but I cannot doubt the cross-section because I cannot fully explain it.
Okay.
It's a number problem. So, because when you look at this, when you look at this, it's really above the data. So we fully agree with the Caspar data in the higher energy range along this dip. That's where we didn't have any data before. That's why we kind of were wondering, is there some systematic error in the data analysis? But we fully agree with that here. And here, Luna is lower and we cannot get the fit down. And I tell you, we tried all sorts of things to get it down. So it's higher than that, and that if it's really higher, then we would be in a better match with the Borexino measurement, which has its own problems. So we're still looking at a slightly open problem here.
Thank you.
Okay, thanks. Any more questions? I can ask something before you think. Okay, so you talked about these neutrinos, neutrino observations, and everything. It seems that they nicely agree, but there's still some more work to be done. Can somebody do something similar by using high-loss seismology data?
Oh yeah,
use high-loss.
Not in the reaction rate, but in the measurement of the abundances. So they look at helioseismology and try to interpret that, and that's led to some discrepancies between the standard solar model and the helioseismological data. So,
but these kind of data have not been used to constrain reaction rates.
No, indirectly, you could do that when you take their data by face value. Then you can basically calculate back the reaction rates.
Mm-hmm. Okay. I don't see any questions in the chat. I don't see any hands. I guess I'll ask one more. So I think in the next slide, there was one data point at around, no, maybe two previous ones. Maybe one, yes, there. So on the right, the next one. Yeah, so on the right-hand side, at around 0.89 or something, there are two data points and they seem to have like very large uncertainties.
This?
No, the other side, the right-hand side. Here, yeah, exactly there. So there are two data in these. So what's going on there?
To be honest,
is it something like, because it seems it's a high energy region, so it shouldn't have such large uncertainty there.
Yeah, probably they just didn't run long enough.
Okay.
So the aim for that experiment, I mean, we did a lot of these data are previous data, and then the goal was mainly to look at the energy range.
I see. Okay. Jana has a question. Anna? I think she's stuck.
Just curious about the future.
I think your connection is so good, Anna.
Yeah.
I only get fractions.
Yeah, me too. Okay, so Gianluca, you can ask your question now, and then we can go back to Anna.
Yeah, no, I have one only to acknowledge the very nice work that the Michael has done with this team, and actually for the ground state transition. So I want only to point out that there is an extra problem because of the fact that it is not easy going down in energy to detect, not only because of it is the ground state, so the cross section is decreasing very much, but also because of the branchings and the subsequent summing correction that one has to do. And in this particular case, the ground state transition is very small, and therefore you have to correct very much for summing in, which is a bit complicated to explain. But going down in energy, you have the double problem that to know the ground state transition, you should detect very carefully also the other transition, and you have to subtract the contribution. Therefore, the best approach would be something similar that has been done by Caspar, to measure with the same setup, covering the largest energy possible, and detecting all transitions and doing so. That basically what has been done by Caspar, but maybe pushing a bit down, trying to cover the very low energy side that has been covered in Luna. But basically, I am happy that at the end we agreed more or less with the results.
Okay, thanks for the comment. Okay, Livia.
Can you hear me?
Yes.
Yeah.
Yes. Okay. Thanks a lot for this complete overview on the problem. And just a question: do you believe, Michael, there could be some effect due to electron screening at this very low energies, or if in some way they can affect your evaluation?
Not at 500 kV. At lower energies, you expect very low energies. You expect the electron screening, but not at 500 kV. I don't know what it is. So the next goal will be angular distributions to see if there's any change. If there's a change in angular distribution, that might give you an indication of some resonance structure which was not known, or some interference effects or things like that. But screening would actually enhance the cross-section artificially and not reduce it.
Thanks again.
Thank you. Anna, can you try again maybe to ask your question?
Can you hear me now?
Yeah, it's perfect
Yeah.
now.
I was just curious about the future of underground measurements in the US. Are there plans to upgrade Caspar or some other new facility?
Yeah, there are plans, but there's no funding. So we have several times we had successful proposals, and for one time it was a sequester which sort of killed it, whatever it was, 10 years ago, and it's always a funding issue to build, because it's expensive. You know, you have to do excavation and things like that. And we were nearly successful 2 years ago, but then last year it looked also very good, but then NSF pulled the plug because of limited funding and things like that, without review, I should say. So it's really challenging, and I take a rather dim view on the future. I think we still have a lot of flexibility to do experiments, but you know, fixing an old accelerator is like fixing an old car. It takes more and more time to fix rather than run experiments. So that's why that's literally the reason why I'm here in Europe, to see if there's collaboration possible with the Luna group, etc. So what are the options? So there's no final decision yet, but we will have to see.
Interesting. Thanks.
Welcome. Okay, any more questions for Michael? I don't see anything. I'll ask one more and then we're done. So if we take all these latest new facilities like JINA and the new Luna, how many of those are capable of measuring down to what the 2005 paper did? So that would be nice to have like another data set in this end to see if they agree or disagree.
So yeah, Luna expanded towards higher energy.
Yeah.
Now, so they still have Luna 400, which is certainly capable to measure at lower energies. And the JINA facility in China, it's a very powerful machine. It's actually very impressive. I've been been there a couple of times, and they recently measured carbon-13 alpha N, pretty much with the same quality and with the same results. I mean, there's some details as Luna, so you can see that's a comparable machine. And they, since they don't have a higher energy accelerator, I would assume that they plan to go to lower energies.
Okay,
And
Gianluca, I guess,
they're
has a
very
comment
ambitious.
about Luna.
Yeah,
Gianluca?
yes, is a common just on the way of what Michael's saying, just to specify that the new machine, the new 3 megawatt machine has been designed to have a good overlap and to get the best output down to 300 kV, just to have a connection with Luna 400 that will be not dismounted, but we will keep it running. And the idea is to have the possibility to build common setup, and in case like nitrogen 14p gamma, to measure from very low energy up to the highest energy possible to cover the whole energy.
Okay, that's great. Looking forward.
Yeah.
Okay, so I don't see any other questions. So let's thank again Professor Wiescher for his wonderful talk, and all of you for joining tonight, or today actually. It was a great term. I guess I'll see you around. There's also the JINA Frontiers meeting in a couple of weeks. So hopefully we will see each other in person. Take care and see you again.
Okay,
Bye-bye.
thanks. Bye.
Thank you, everyone. Bye.
Bye-bye.
Bye.